Hello everyone, welcome back to the course on architecture design of ICs. So, in the last class we are discussing about this carry select adder, and from that carry select adder what we have that means come to know that again we can, that means share the input, and based on the, that means predicting the carry input, which will be nothing but that 0 and 1. Okay. So, we will pre-compute the values of this using this full adder cell, one for 0 considering this carry input bit of 0 and another considering for carry input bit of 1. Okay. So, we will pre-compute that, and that means whenever this the previous stage carry, based on that we will take the decision whether that previous that means stage carry, whether that is 0 or 1. Based on that we will select which input, or that means what combination that will be passed. Okay. So, based on that we have developed, or we have that means tries to develop this conditional sum adder, which is that means the fastest adder among all these adders what we have, that means learned till now. So, we were discussing about this conditional 8-bit conditional sum adder. So, what that means what we are seeing, okay, that in the last section, okay. So, as there is this C in, we know from the beginning. Okay. So, that is why actually I need only one full adder cell for this LSB position, which is x 0, and for adding this x 0 with y 0. Okay. So, whenever we are adding x 0 and y 0, at that time what I will get? I will get one carry output from this particular full adder cell and the sum 0. Okay. Then for the y 1 and x 1, you see there are two full adder. So, one, and these two inputs are shared among them. Okay. One actually full adder cell that computes the, considering the carry input bit 0 to it, and another full adder cell actually computes the sum and carry based on this, considering the carry input bit of 1. That means, whenever I am computing this particular cell, at that time I am also computing these two full adder cell, as these inputs are already available to me, all the inputs. Okay. So, that means for this particular y 1 and x 1, addition of y 1 and x 1, I will get these two full adder cell running in parallel, considering 0 carry for one or 1 carry for another one. So, basically in addition, in ripple carry addition or in any other addition, what happens? The previous stage generated carry that affects the current stage, that means sum and the carry both. Okay. So, here what we are doing? We are previously from the beginning we are that means calculating the values of, considering as carry input bit, that is of 1 bit, that will be that can, and we are doing this binary addition. So, that means that cannot go beyond 0 or 1. Okay. So, that is why what we are doing, we are pre-computing these values considering the carry input bit to 0 and 1. So, whenever I am getting at this previous that means carry is C1, based on that we are taking the decision that which output from this two particular full adder cell that will pass. So, if the carry signal is 0, so at that time this full adder cell will pass these values. Otherwise, if this value is 1, then this full adder cell values will pass, that is values means this sum and carry will pass from these multiplexers. Okay. So, that means now if I just, this indicates the concatenation. So, from here now I will get this S 1, here from this I am getting the sum S 0, and from this particular multiplexer I am getting sum 1, and another of that I will get the, that means this stage generated carry, which is this C 2. Now, next go to the, that means third bit. Now, for y 2 and x 2. Okay. So, then again you consider this y 2 and x 2, y 2 considering 0 and y 1 considering, sorry, y 2 and x 2 two full adder cell, one considering 0 carry in and another considering 1 carry in, right. Then again for y3 and x3, again I have to do 2, that means I have to use 2 full adder cell considering one of 0, another of 1. So then for this particular stage, this also can generate the carry. Here what is happening? For this only, as there is only one full adder cell, so that can only generate 1 carry. But here what is happening? I am only getting 1 and 1, suppose I am getting for this 2 1 and 1 and the carry from here, that is 1. Okay. So, that means now I am adding 1 1 1, 3 ones, and then again for y2 and x2, if I am getting again 1 and 1, that will also produce another 1. That means for this particular case 2 carry will be come to this affecting this particular case. Okay. So, that is why actually the previous stage carry initially that will affect. So, that means 1 carry that will be generated from this particular stage and 1 carry will be generated from this particular case. Okay. So, then one multiplexer I will use for y3 and x3, which will considering this particular, that means 0, that means carry, and another one is for the, if that means the for considering y2 and x2 of 1. Okay. So, now we are doing this two particular multiplexers for y2 and x2, which is just the previous carry of this y3 and x3. Okay. So, we have computed these two, that means for multiplexer of these two we have calculated for the previous stage carry. But again another carry, what I said, that another carry can generate, which is this C2, that will also affect to this particular stage. So, based on that, again these two multiplexer will pass through another multiplexer where C2 will take the decision. If this C2 is 1, then this particular group will pass, otherwise if this is 1, then this group will pass. Okay. So, that means now I can generate the carry output bit and another input, which is this 2 bit. Basically what I am getting? I am getting 2 bit here. Why 2 bit? One sum from this, another sum from this. Okay. So, that means I have to, that means as this sum is also concatenated and this sum is also concatenated with this particular sums. So, that means I will get 2 sum here and that will concatenate with the previous 2, and from here I can calculate or I can compute this last 4 bit of sum, and this is the, that means corresponding carry out bit. Then again, as this is for, actually if I just stop here, this is for 4 bit conditional sum adder. Now, if I just go to the, that means then what I actually my intention is to design, that is 8 bit conditional sum adder. So, then again for y4 and y5. Okay. So, y4 and y5, again this kind of architecture, that means the same logic will be applicable for y4 and x4, sorry, y4 and y5 or x5 or that means x4. So, this architecture then I will just copy here. Then same thing will happen for this 6th position and 7th position. Okay. So, if I say that this is the 0th position, this is 1, then 2, then 3, then 4, then 5, then 6 and 7. So, in a group, so this will affect this, this will affect this, this will affect this, this will affect this. So, in the beginning we can, that means draw this particular circuit for this, for even 2 of them, and then from this for the odd one we will have 2 full adder cell along with these multiplexers. Okay. So, then the carry which is generated from this particular cell, what logic we have followed here? That means this particular carry that will affect this. Okay. So, here this particular cell's carry that will again affect to this particular cell. So, that is why I need this multiplexers, these two multiplexers for these two multiplexers. Okay. So, then again these two multiplexer again, that means actually where from that another carry will be generated, another carry which is the, that means from this fourth bit there is another carry. So, then that again that will take the final output, or that will be affecting the carry output generated from this particular blocks. Okay. So, we will take the final output which is nothing but this 4 bit for this particular 4, that means considering this x 4 to that means x 7, I will get 4 some bit here and this carry bit of 1 here. Okay. So, based on this particular this carry output bit, this will select which of this that sum we will choose, and how we are coming to this, that means concluding to this particular point, that which one will be selected. If you just go back and that means reverse computation, if you do, you just see that based on this that means the adjacent stage that affects the next stage, and that next, that means previous to previous stage carry also, that means that also affects the current stage sum and carry computation. Okay. So, based on this particular circuit, now we can calculate the corresponding sum, which is, so 4 bit I am getting from here and another 4 bit I am getting from this particular block. So, if I concatenate both of, that means these two, then I will get 8 bit sum and 1 carry output bit. Okay. So, this is the 8 bit conditional sum adder. So, if you see, that means in this two particular case, so what is the level of marks I need finally? So, the level of marks which I need, that is log 2 base, if I consider, that means n. Okay. So, for n bit conditional sum, how many how many this multiplexer cells I require? That will be log 2 base n. So, if n is 8, so that means 3 level of multiplexer I require. So, if n equals to 16, so at that time I require what? I require 4 level of multiplexers. So, at that time what will happen? That means if I want to, that means this circuit, if I just want to that means convert from to the 16 bit conditional sum adder. So, at that time what will happen? At the very this particular carry out, the carry out which is, that means generated from this particular cell. So, that will affect the 4th multiplexer if I consider 16 bit conditional sum adder. This rest of the circuit will be that means not, it will be like just like same. So, that means for this just next to next, it will follow something like this, then again like this, and then again like this. Okay. So, that means 2 3 4 2 3 4, this again it will continue, and finally this carry will select the final output bit. That means, whenever I will compute these particular things, as I am following this 3 level at the maximum, that means MSB side. So, for the 16 bit, for y 15 and x 15, along with this y 14 and x 14, I will get 4 levels of multiplexer over here. So, here what is the, that means this if I consider the this delay term. Okay. So, then what is the, that means maximum delay over here? What is the maximum delay over here? So, one of the path which is following, that is from y0 to the corresponding particular path. Okay. So, one path is this this full adder, then 1 multiplexer, then 2 multiplexer, then 3 multiplexer.
Okay. Then again if I choose this particular path, then from this input one full adder cell, then multiplexer, then multiplexer, then multiplexer. Okay. So, if I from this particular cell, if I just compute what is the maximum critical path, one full adder cell, then this two, then again this is coming to that means this is coming to this, that means one full adder cell, one multiplexer, two multiplexer, three multiplexer. So, that means again I am following the corresponding that means this delay for this particular 8 bit conditional sum adder is one full adder cell delay plus 3 that means 2 is to 1 multiplexer delay. So, if I consider 16 bit, so at that time 1 full adder delay and 4 multiplexer delay. That means though I am increasing the number of that means if I am increasing the number of bits, but my delay that is not increasing that much. What I am increasing? Only I am for 32 bit, there will be only that means the delay increment, that will be just one multiplexer delay. But the thing is that at that time I am getting the benefit in terms of delay, but at what cost? I am putting extra hardware, that means I am putting extra multiplexer in this circuit or this full adder cell, so that I am that means making it redundant. The computation whenever we are doing this pre-computation or pre-assumption based computing we are doing, so at that time we are putting redundancy to the circuit. Okay. So, that means whenever we are putting redundancy, that means it consumes more area than the original one. So, that means in this particular case I am getting the benefit of delay with respect to losing the area. So, if I am increasing the area, I can say that, or I can that means roughly say that I also can increase the corresponding power consumption, that means switching power consumption, as I am putting more number of that means logic elements here. Okay. So, that means switching power consumption is one of the part of this dynamic power consumption, right. So, switching power consumption if it is increases, that means at that time I can say that okay, dynamic power consumption is also increasing for this particular circuit. But for this parallel implementation of this, as I am doing parallel implementation, so that has again some of its that means advantage for power consumption, making the power consumption at the lower side. Okay. So, from this particular, unless and until we are simulating it, that means we are implementing it in hardware, we cannot say that okay, the power consumption is basically increasing, but just from the observation point I can say that as switching power is increasing, so dynamic power is increasing, so power is increasing, that I can say only. Okay. So, if I take one example of this, okay. So, if I take one example how it that means computes, so at that time it will be much more easier to you. So, this is considering what? This is considering 4 bit 16 bit addition operation, okay, where x value is this one and the y value is this one. Okay. So, here you see the corresponding, that means number of levels which is required, that is only 4. In the 5th I will get the output. So, that means 4th, if I just like if I just mention it like a cycle. So, at that time 4th cycle I need to compute the 16 bit addition using this conditional sum adder. So, whenever if I consider this particular example, so at that time for the LSB position, if I just go back, that means sorry, if I just go back for this is y0 and x0 and this will be added with C in. So, here C in is 0. So, that means whenever 1 and 0 is there as the input of x 0 and y 0, at that time sum will be 1 and carry will be 0. For the y 1 position, y 1 x 1 position, what will happen? 1 will compute, if I just again go back. So, this again we will get two set of sum and carry, one considering carry input bit of 0 and one considering the carry input bit of 1. So, that means now I will get two set, as this x 1 and y 1 they are 0 1. Okay. So, for 0 sum is 1, carry is 0. If carry input bit is 1, so at that time sum is 0, carry output bit that is 1. Okay. And from this particular point, if I see, that means now if you just go back, so based on this what it will select? It will select as this carry output bit, it is 0. So, it will choose which value? This value, considering the carry input bit of 0. So, that means now in this particular case 1 and 0 that will be selected from this particular point, that means this C 2 will be 0 and S 1 will be 1. Okay. Then that means S 1 is 1 and carry C 2 is 0. Then for the, that means second position. Okay. So, y 2 and x 2, for y 2 and x 2, what is the value? Y 2 and x 2, I am getting for 1 1, I will get sum equals to 0, carry equals to 1, for 1 1 and carry 1. So, both are 1. Okay. So, now whatever is then that means now if you just go back, so this C 3 and this C 3, now it will take the decision. Okay. So, that means it will take the decision of what? It will take the decision for y 3 and x 3 sum selection or the carry generation selection. That means for y 3 and x 3, consider as this is 1 0. So, considering 0 I will get 1 0, considering 1 in carry input I will get 0 and 1, right. So, whenever I will choose, whenever I will come to this particular point, so at that time what will be selected here, what it will be selected from here? It will be selecting this as the previous carry here, that is 1, sorry, yes, the previous carry is 1, that means it will choose 0 and 1. And for this particular case is also the carry output bit, that is 1. That means again it will also choose 0 and 1. Okay. So, that means in both of this case, as this C 3 is 1, so it will choose 0 and 1, for this also 0 and 1, for this also 0 and 1. Okay. Then 0 and 1, then 0 and 1. Okay. So, now this again this will be selected based on what? Among which set I will choose? Which set I will choose? It will be selected this 0 1 or 0 1, this will be selected based on this particular signal. So, what was my C 2? C 2 is basically coming from this particular point. So, C 2 is 0, that means it will select 0 and 1 over here. So, that means the carry output bit or C 4 value is 1 here, whether this S 3 as this is of 2 bit. Okay. So, here 2 bit means both of this is basically 0 and 0, this is 0 and 0. So, I will get S 3 and S 2 of 0 and 0. So, that means S3 of 0 and 0, and for these two particular case the sum is 1 and 1. Okay. So, that means now I am getting S3 down to 0, they are 0 0 1 1. Okay. So, then again come to this particular point. For computation of this particular circuit, where from we have to start? We have to start from this particular cell. Okay. So, that means here for y4 and x4, for y4 and x4, so this is up to this. So, for y4 and x4, for 0 1, this is sum is 1, this is 0, other case considering the carry input bit of 1, they are 0 and 1, right. Then again this will affect what? To the 5 position. So, in 5 position what are they? 1 1 means 0 and 1, 1 and 1. So, that means considering the carry input bit of 1, that is 1 1 1, and for considering carry input bit of 0, that is 0 1. Okay. So, now based on this, for carry input bit of 0, what I will choose for this? That is 0 1. For considering the carry output of this particular stage 1, we will choose 1 1 over here. Okay. So, then again you just come to this point. So, that means now this 2 bit, if I consider this 2 bit, then what will be the bit? What bit I will consider? They are, that means for 0 and 1. Okay. Why? Because this bit is the output of carry of from this. If I just go back, the output carry from this particular point, it is from this is computing 0 1, and for this is choosing 1 1. Okay. And based on this I will get what? I will get 1, that means these two combination will be what? 1 sum for sum, from here I am getting 1 and from here also I am getting 1, that means 1 and 1, and for this is 0, this will be for 4 5, this will be 0 and 1. Okay. So, the sum is 1 over here. Okay. So, that means 1 I will choose here, and for 5th I will choose 0 here. Okay. For what? For this particular stage. Okay. Now, again I will generate the carry output bit 1 here and 1 here. If you see that for both the case 5th, these two carry output bit of carry, there both are 1. Okay. So, now that means now this again it will affect what? This 1 and 1, that will affect to the 6 and 7 position. So, again something in this manner we have to find out, that means this x6 and s7, sorry s6 and y6, they will affect this y7 and x7. Then again from this multiplexer we will get 2 bit group. 2 bit group means one from this particular sum and one from the sum of this particular stage. Okay. So, then again they will be selected based on the carry which is generated from, if I combine, that means if I take this as a group. So, from this group whatever the carry is generated, so that will affect to this. And then if I consider these 4 as a group, so the combination of this, the carry generated from this 4, that will come to effect at this final multiplexer stage. Okay. So, I will get concatenate, if I concatenate 1 and 1, then I will get 2. If I concatenate this 2 and this 2, I will get from these two multiplexer, I will get 4 output bit. Okay. So, then this 4 output bit will come here and I am getting 4 output bit here. So, then again they will concatenate and we will produce the 8 bit sum over here, and the carry output bit from this particular stage, which is dependent on this whatever signal I am producing for this particular group, which is nothing but this C4. Okay. So, in this manner we can compute this 16 bit or any bit, that means here it is 8 bit. So, if I just want to that means make it 10 bit. So, for 10 bit also it will have 4 of these multiplexers. Okay. So, in this manner we have to design the corresponding conditional, or we can design the corresponding conditional sum adder. Okay. So, this is the, that means we are if we are taking the one example. So, at that time, so in this manner, as this is of 16 bit. So, in this manner it has been generated, then based on that, this is the, that means this is the first level of output. Okay. Then this is the second level of output, and this is the third level of output, and in the fourth level we are getting the final output bit. That means the addition results of this, considering the value of x and y of these two. Okay. So, for today's class up to this one. Okay. Then again there are various type of that means fast adder architecture, which are already there in the, that means literatures. So, we will discuss with that what type of other architecture, adder architectures are available, and that means how their that means how they are implemented, considering the speed or power as the major constant or area as the major constant, that we will see in the future classes. So, thank you for today.